Hello everyone, given the stupid amount of heat I'm sitting in and the hopefully not too audible background humming of the air conditioning, I thought it might be appropriate to talk about how air conditioning and heat pumps work. So today I am going to explain to you how a heat pump as found in a fridge or an air conditioning works, what other kinds of heat pumps there are, and theory and practice, and the basics behind what they are. Now, we probably almost all know that heat can never really be destroyed. That's basic thermodynamics. Once heat is created, you can create heat, you can turn any other form of energy into heat energy and use it to heat things up. That's how most heatings work, but the opposite is not possible. You cannot turn heat energy into any other form of energy. Once it is heat, it remains as heat, and the amount of heat in a closed system can never be reduced, and in a non-closed system heat can simply be transferred to the outside, but that's it. It can't be destroyed as such. So any cooling system works by either not by not being a closed system. It somehow has to transfer heat to the outside or get something relatively cold from the outside. Now, of course, you can keep delivering a coolant that is cold and or pressurized, like liquid nitrogen, and just pour it over something to cool it. Or you can pump heat. Now, it's also thermodynamics that naturally heat flows from warm to cold in whatever way. The speed at which it does this, the rate at which it does this, depends on what is between the two ends, what kind of thermal gradient you have, and other factors. But generally, heat transverses from a hot object to a colder object, and you can actually gain energy from this. The not only heat itself is a form of energy, but the heat difference, the temperature difference, the temperature gradient is also a form of energy. When heat flows from a warm place to a cold place, you can actually slow this down and gain energy from the thermal gradient. And the other way around, you can use energy work to pump heat from a cold place to a warmer place against its natural flow. But of course, this uses up energy, and in the end, you kind of create more heat than you get rid of. But you can create this heat in a warmer place. You can push the heat towards a warm place and then dispel of it, and air that, for example, in air that you went out of the window in the case of air conditioning, or simply to the back side in the case of a fridge. Now, there are different ways this can work. There is, but it usually, with the exception of some electric effects, it usually requires some form of coolant or refrigerant that can either take in or dispel heat without changing temperature, or change temperature without actually taking in heat. Now, there are two basic ways this can work. The most common way is using a liquid coolant and depressurizing or expanding it to cool it down, then taking in heat as it is cold from some other medium and heat sink, thus condensing it, turning it into a gas. Then you can pressurize that gas to heat it up. Then you can give off heat as it is warm, and you can give off heat through some heat sink or other medium. and then you can give off so much heat that it condensates and turns back into a liquid. Then you can expand and depressurize it again, and the whole cycle begins over. The actual cooling liquid stays the same. It's never exchanged. It just circulates and turns into a gas and back into a liquid. But it is cooled down and heated up without actually adding or taking out heat. And then once it is hot or cold, heat is actually added or taken out in addition, thus keeping the whole cycle an overall temperature change of 0, but you can take in heat as it is cold and give off heat as it is hot, and thus you can pump heat through an additional thermal gradient and pump heat from a cold place to a hot place. Now the slightly less extreme but nowadays technically much less practical and much less used practice would be to just take a gas or liquid without changing its state and just pressurizing it and expanding it to change the temperature without adding or taking away heat, and then actually adding and taking away heat in the other two steps. Now, you can do this. You can expand the gas and thus cool it down below its original point and then take in heat, then pressurize it again, then give off heat as it is now hotter, then begin the cycle anew. But it's basically the same process and much less effective and slightly simpler to do, and it doesn't find any use nowadays. It does find use in a slightly modified form where you don't actually have a pump but rather have a vibrating tube. It's called thermoacoustic cooling. This is used in very low temperature but long duration freezing processes, as in cryogenic labs, for example. You basically have a tube and air in it, and the device itself is kind of a fringe case. It's kind of a solid state device, but not really. It does move, but it doesn't really have moving parts. It just vibrates elastically. So it's a rather long duration. It's a rather simple device as such. It has really just one part, a tube, and you kind of have to put it in move. You need a tube and a speaker, or a tube and a piezoelectric device, something. But it's really simple. It can reach low temperatures with the right gases, and it can provide kind of good cooling. It's not as effective, but it works at lower temperatures. It's quite reliable, and the device itself is really simple. And then there are true solid-state heat pumps that are thermoelectric or thermomagnetic. The thermoelectric ones are actually in use for small-scale applications and also some scientific applications, but we mostly know them as Peltier elements for small-scale applications. These have the nice side effect that they can be used both ways. The Peltier element can actually be used to either pump heat, that is, if you apply a voltage to the element, a current goes through the element, and one side heats up, the other side cools down, and heat is pumped through the element from the cold side to the hot side. The which side is which depending on the polarity of the voltage you apply to it. But you can also use it the other way around. If you have a hot object and a cold object, you can basically heat up one side and cool the other side down, and then gain electricity from it, like a solid-state Stirling engine, basically. Now, these are easy in build, as they are basically just two slightly different materials, and you put a voltage to them, and they output a thermal gradient perpendicular to the joining of the two materials. But the way they actually work internally on an atomic scale is actually a bit more complicated, but to simplify it, it basically works like an electric motor and an electric generator with an additional power input, then amplifying a signal that is essentially the erratic motion of the heat on one side, to put it out on the other side where it is actually amplified to create more heat there, and cool down the other side while amplifying the motion with additional energy. That is extremely simplified, but it's the kind of understandable way of how this works. Now the thermomagnetic effect is actually much less interesting. It actually just works like the old aerodynamic or thermoacoustic or pressure-based heat pump. It just heats something up or cools something down without actually adding heat. It's the effect that if you have a conductive material and you place it in a strong magnetic field, the material will increase in temperature even if you don't actually add any energy in the form of heat. And if you remove it, the temperature will be reduced even without taking out any heat energy, and you can then again build a cycle, place it in a magnetic field so it gets warmer, sink out the heat, remove it from the magnetic field, pull heat in, and then you have a cycle like the old pressure-based or condensation-based heat pump. Now, in addition to this, there are, of course, cooling systems based on just inputting something cold. You can, of course, many air conditionings actually have a additional feature where you can, additionally to the heat pump cycle inside it, that just takes in room temperature air or moderate air and outputs it as part hot air and part cold air, and directs the cold air hopefully towards you and the hot air out the window. There's also an additional feature where you can just add a small tank of water. You can fill it up wherever you like, and that water then gets used up slowly as it condenses and cools down the air. I actually have this kind of additional little feature in my air conditioning. It it's built into most stationary ground-based air conditionings. The ones that you can install to the window or uh, like hang onto the roof or onto the wall usually don't have this, as it would just be impractical and unsafe to have a water barrel that you have to put into a wall mounted device. But the ones that are like freestanding on the ground usually have this kind of additional little extra cooling feature if you have water to refill it with. Fridges usually don't have this, as they don't really need that much cooling power. Fridges are usually well isolated and just need a tiny bit of cooling to or heat pumping to keep them cold. And of course, if you open them and put in something, they need a little more power to cool that down. But they don't really need that powerful heat pumps at all. So it's usually only found in air conditionings. Now, I hope this little overview was interesting, and thanks for watching.